Fundamental electrical concepts. Electric charge, Q, characteristic of subatomic particles that determines their electromagnetic interactions. An electron has a -1.60211019 coulomb charge. The rate of flow of charged particles is called current. Current equals number of electrons that pass in 1 second, charge/electron, 1 ampere equals 6.2421018 E/SEC, minus 1.60210-19 coulomb/E. Notice that an ampere equals coulomb/second. The negative sign indicates that the current inside is actually flowing in the opposite direction of the electron flow. Electrons current. Current I equals dq/dt, the derivative or slope of the charge when plotted against time in seconds. Q equals indefinite integral I dt, the integral or area under the current when plotted against time in seconds. 4321 current amps 5 SEC. Q delivered in 0 to 5 SEC equals 12.5 coulombs. AC and DC current. DC current has a constant value. AC current has a value that changes sinusoidally. Notice that AC current changes in value and direction. No net charge is transferred. Why does current flow? A voltage source provides the energy, or work, required to produce a current. Volts equals joules/coulomb equals dW/dq. A source takes charged particles, usually electrons, and raises their potential so they flow out of one terminal into and through a transducer, light bulb or motor, on their way back to the source's other terminal. Terms to remember: the source can be any source of electrical energy. In practice, there are 3 general possibilities. It can be a battery, an electrical generator, or some sort of electronic power supply. The load is any device or circuit powered by electricity. It can be as simple as a light bulb or as complex as a modern high-speed computer. Path, a wire or pathway which will allow electron to flow throughout a circuit. Electricity can be described as the flow of charged particles. If the particles accumulate on an object, we term this static electricity. Direct current, an electrical current that travels in one direction and used within the computer's electronic circuits. Alternating current, the common form of electricity from power plant to home/office. Its direction is reversed 60 times per second. Circuit is a conducting path for electrons. Voltage is a measure of the potential energy that causes a current to flow through a transducer in a circuit. Voltage is always measured as a difference with respect to an arbitrary common point called ground. Voltage is also known as electromotive force or EMF. Outside engineering. What is Ohm's law? Ohm's law states that, at constant temperature, the electric current flowing in a conducting material is directly proportional to the applied voltage, and inversely proportional to the resistance. Why is Ohm's law important? Ohm's law is the relationship between power, voltage, current, and resistance. These are the very basic electrical units we work with. The principles apply to alternating current, AC, direct current, DC, or radio frequency, RF. Ohm's law I equals V/R. George Simon Ohm, 1787 to 1854, I equals current, amperes, amps, V equals voltage, volts, R equals resistance, ohms. Characteristics of Ohm's law: voltage, difference of potential, electromotive force, ability to do work. Unit of measure: volt symbol V, current, flow of electrons. Unit of measure: ampere symbol I. Resistance, opposition to current flow. Unit of measure: ohm, often seen as the Greek letter omega symbol R. A circuit current flows from the higher voltage terminal of the source into the higher voltage terminal of the transducer before returning to the source and source voltage, I and transducer voltage. The source expends energy and the transducer converts it into something useful, I. Circuit diagram: cell, switch, lamp, wires. Scientists usually draw electric circuits using symbols. Simple circuit: series circuit, all in a row, one path for electricity, one light goes out and the circuit is broken. Parallel circuit, many paths for electricity, one light goes out and the others stay on. Series and parallel circuits. Series circuits, only one end of each component is connected, e.g. Christmas tree lights. Parallel circuits, both ends of a component are connected, e.g. household lighting. Passive devices. A passive transducer device functions only when energized by a source in a circuit. Passive devices can be modeled by a resistance. Passive devices always draw current so that the highest voltage is present on the terminal where the current enters the passive device, and V0, I0. Notice that the voltage is measured across the device. Current is measured through the device. Active devices. Sources expend energy and are considered active devices. Their current normally flows out of their highest voltage terminal. Sometimes, when there are multiple sources in a circuit, one overpowers another, forcing the other to behave in a passive manner. Power. The rate at which energy is transferred from an active source or used by a passive device. P in watts equals dW/dt equals joules/second. P equals VI equals dW/dQ. dQ/dt equals volts. Amps equals watts. W equals indefinite integral P dt. So the energy, work in joules, is equal to the area under the power in watts plotted against time in seconds. Conservation of power. Power is conserved in a circuit. Sigma P equals 0. We associate a positive number for power as power absorbed or used by a passive device. A negative power is associated with an active device delivering power. I plus V. If I equals 1 amp, V equals 5 volts, then passive P equals plus 5 watts, absorbed. If I equals minus 1 amp, V equals 5 volts, then active P equals minus 5 watts, delivered. If I equals minus 1 amp, V equals minus 5 volts, then passive P equals plus 5 watts, absorbed. Example: a battery is 11 volts and as it is charged, it increases to 12 volts, by a current that starts at 2 amps and slowly drops to 0 amps in 10 hours, 36,000 seconds. The power is found by multiplying the current and voltage together at each instant in time. In this case, the battery, a source, is acting like a passive device, absorbing energy. Voltage, current and power. Voltage, current and power. In this second example, we will calculate the amount of resistance, R, in a circuit, given values of voltage, E, and current, I. What is the amount of resistance, R, offered by the lamp? In the last example, we will calculate the amount of voltage supplied by a battery, given values of current, I, and resistance, R. What is the amount of voltage provided by the battery? Resistance, property of a device that indicates how freely it will allow current to flow given a specific voltage applied. If low in value, current flows more freely. Measured in ohms, omega equals V/A or K. Omega equals V/mA. I obeys the passive sign plus convention. V. If I0, then V0 R equals or V equals IR. This is Ohm's law. Voltage, current. Resistors. Resistors are devices that are used in a variety of circuits to make the currents and voltages what you desire. They are color-coded and come in various tolerances, plus or minus 1%, plus or minus 5%, and plus or minus 10% are most common. Resistor color code http://www.lxb.com/t_resist.htm56*10k equals 560k 237 *1 equals 237. Conductance, G. Conductance is the reciprocal of resistance. Its unit is the Siemens equals amp/volts equals 1/omega. G equals I/V equals 1/R. An equivalent measure of how freely a current is allowed to flow in a device. Resistivity, ρ, property of a material that indicates how much it will oppose current flow. R equals ρ length, cross-sectional area, units are ohms meters, omega m. As the wire gets bigger, so does the cross-section, making the resistance smaller. As the length gets longer, the resistance goes up proportionately. Conductors, materials with electrons that are loosely bound to the nucleus and move easily, usually one electron in the outer shell. Their low resistance goes up as the material is heated, due to the vibration of the atoms interfering with the movement of the electrons. The best conductors are superconductors at temperatures near 0 Kelvin. Semiconductors, materials with electrons that are bound more tightly than conductors, usually 4 electrons in the outer shell. Impurities are added in controlled amounts to adjust the resistivity down. Semiconductors become better conductors at higher temperatures because the added energy frees up more electrons, even though the electron flow is impeded by the increased atomic vibration. Insulators, materials that have all 8 electrons in the outer shell tightly bound to the nucleus. It takes high temperatures or very high electric fields to break the atomic bonds to free up electrons to conduct a current. Very high resistivities and resistances. Resistivity of materials: glass, gold, silver, silicon, aluminum, copper. Put a number 1 beside the material that is the best conductor, a 2 next to the material next most conductive, etc.